we will be discussing now transportation of tufts. We all know that blow-room consists of a series of machines connected together, and we need to transport the tuft from one machine to the other. Now, what are the means of transport? There are two means. One is mechanical, that is with the help of conveyor belt or lattice, and the second is by pneumatic means. So, basically two ways to transport the tufts. One is purely by mechanical means with the help of conveyor belt or lattice, the other one is pneumatic transport. Now, let us focus on the mechanical transport, which is with the help of conveyor belt. Now, conveyor belt is basically an endless belt that runs over two or over a set of pulleys, and one of the pulleys act as a driver pulley. As you see the diagram on the right hand side, there is a driver pulley and there is a driven pulley, and there is an endless belt which is connecting these two pulleys. This is the typical conveyor belt, which is also used in other places. Now, this kind of belt we can run at a slightly higher speed, that is the advantage with this endless conveyor belt. And the lattice, if you look at it, the lattice is made of wooden cross bars like this blue rectangles that you see in the diagram. These are basically wooden bars, or these are the wooden bars, and they are screwed together or riveted to the endless circulating belt. So, you can see it, the diagram on the right hand side, that while the surface of a normal conveyor is flat and smooth, and that of the lattice is having raised portion, and these are basically wooden bars which are screwed to the belt. So, these are the difference between these two, and if we try to understand the advantages and disadvantages between them, then the conveyor belt advantage is it enables high speed. We can run them at a slightly higher speed, but the disadvantage is the material slips on it, because the surface of the belt is very smooth, and there is a possibility that the coefficient of friction between the cotton and the belt could be so low that the belt will move, but the stack of cotton which rests on it may not move. That is the negative aspect of the conveyor belt. So, but still it is used in feed or horizontal conveyor in the openers or hopper feeders. This kind of belts are in use. The lattice type, what we have discussed, lattice with a wooden crossbar that we have seen, speed is generally slow, generally it is 1 to 3 meters per minute, that is the typical speed. So, speed wise it cannot be run at very high speed. So, wherever we need to transport the material at a slow speed, we can make use of it, and the best part of it is that the material does not slip on it because of this raised bar. So, these are used with horizontal feed lattice and short transport belt within the machines. We make use of this kind of lattice with wooden bar. The other is the lattice may have steel pikes mounted on the crossbar at an angle, and if you try to recall the bale opening machines, you must have seen that there are spikes on it, and the spikes are at an angle. The advantage is we can run it at a higher speed and the chances of material to slip is also less. The spikes will be penetrating the tuft and will physically hold the tuft and then it will move forward. So, it is used in bale opening machines for lifting the tufts. So, these are the mechanical way of transportation of tuft. Now, if we try to go for a little analysis of the conveyor, then on the right hand side you see the conveyor is shown and at the bottom of it there is a free body diagram of the conveyor. Let us say the weight of tuft on a horizontal conveyor we are discussing now, the weight is total weight is W. The coefficient of friction between the conveyor and the guide rollers is mu 1. So, the conveyor, it could be a long conveyor and there are supporting guide bars or guide rollers could be there, like it is shown in this diagram also in the lower diagram. Let us say coefficient of friction between these two is mu 1 and the static coefficient of friction between the driving pulley and the conveyor is mu 2. Okay. Now, the force on the idler pulley, so there are two pulleys. So, this pulley is the driver pulley and the other pulley which is driven pulley we can call it idler pulley. And what we do, we push the idler pulley on the left hand side in order to tighten the conveyor belt. If the conveyor belt is loose and the driver pulley runs, the belt is going to slip. Therefore, we have to apply some amount of force as shown in the diagram F. Some force has to be applied. So, we have to basically pull the idler pulley on the left hand side, so that there is some tension in the conveyor. And let us say the weight of the conveyor is W. Okay. So, from the free body diagram as shown in the right hand side, we can say the total normal force which is acting is W, capital W plus small w, and therefore, the tension T1 will be how much? It is going to be T3, the tension at the other end, plus we have to overcome the frictional force which is W plus small w multiplied by mu 1. So, T1 therefore, is greater than T3. From there, let us now focus on the tension T2 and T3. So, T2 and T3 is supporting the force F and the angle of drag being 180 degree. Therefore, what will happen? T3 is always equal to T2 and summation of T2 and T3 is going to be F, that is the pull that we exert on the idler pulley, and hence T3 and T2 is going to be F by 2. So, now we can find out how much is T1 from the previous equation. So, T1 becomes F by 2 plus W plus small w into mu 1, that is the tension T1 that will be. So, we can say therefore, that the tension on the upper part of the conveyor is not constant along its length. On the left hand side, tension is less, on the right hand side tension is more, because it is carrying a certain amount of load. Now, to avoid slippage of the driving pulley, the condition for impending slippage is T impending is how much? It will be T2 into to the power mu 2 into pi, where mu 2 is the frictional coefficient between the driver pulley and the belt. So, this is the impending slippage, as long as this T impending, this tension value is greater than T1, the belt is not going to slip. Otherwise, if the T1 rises and it goes beyond T impending, in that case there is a possibility of slippage. Now, to prevent slippage, what are the means we have? If we look at this equation 7, we can find out how to increase T impending value. So, T impending value depends upon what? It depends upon T2, and T2 in turn depends upon the value F. Therefore, increasing tension F will be helping us to reduce the possibilities of slippage. The other thing is increasing the frictional coefficient mu 2 between conveyor and the driver pulley. So, that is another way of changing, but once we have decided the material of a pulley and also we have fixed a conveyor, then mu 2 cannot be changed. So, but there is a possibility of changing. The other thing is to increase the angle of wrap, that is angle of wrap is how much? In the present case it is exactly pi, that is 180 degree. So, if this wrap can be changed, if we can increase it, in that case also we will be able to reduce the possibility of slippage. Now, how we can increase the value of pi? We can go by a design something like this, and so we can have a roller like here and make this ball go to pass over this. In that case, its angle of wrap can be changed. So, that could be another way of changing the angle of wrap, but generally that is what is not changed. In the normal circumstances in the industry, in our textile mills, we try to avoid slippage by increasing the tension on the conveyor belt, that is by increasing the value of F. Okay. So, that is all about your mechanical means of transport. Now, we have to discuss pneumatic conveying system. Pneumatic conveying system is also very important in the spinning, also in weaving also as well. In spinning we are transporting tuft from one machine to the other, we may be transporting fibers, and let us say in the case of rotor spinning, which you will learn later on, and in the case of air jet looms we transport the yarn from one end of the loom to the other end. So, there are many examples where pneumatic transport is used, not only in textile, but also in other industries as well. Okay. So, there are two ways or two phases of pneumatic transport. One is dilute phase of conveying, the other one is dense phase of conveying. In dilute phase, high volume of air at high speed is used for conveying the material, and within this also there could be two modes, suction mode and pressure mode. So, suction mode operates below atmospheric pressure and pressure mode operates above atmospheric pressure. The dense phase of conveying, here low volume air at high pressure are used to transfer nearly solid mass, that is what we do. So, in the case of dilute phase conveying, high volume of air is used at high speed, whereas dense phase of conveying we use low volume of air, but at higher pressure to transfer the solid material. In our case it is mostly dilute phase of conveying, and there also there are two possibilities, one is suction mode of conveying, the other one is pressure mode of conveying. Okay. Now, we will discuss suction mode of conveying. In the suction mode of conveying, what we need? We need a duct whose one end will be open to the atmosphere, so that the air can enter, and the other end must be connected to a suction fan, like it is shown in this diagram. On the right hand end, the suction fan is there, on the left hand end there is a air entry point, and in between the duct is there. So, the suction fan generates negative pressure, and therefore, air will enter from the entry end of the duct. A means also we need to separate tufts from air. Now, in the duct we need another entry point for the tufts. So, there has to be a tuft entry point as shown here in the diagram, and then since the air will carry the tuft towards the right hand side in this case, whenever we reach the destination point of the tuft, we have to have a means to separate out the tuft from air. So, therefore, we need some kind of screen. The fan creates a strong air current, typically 12 to 15 meters per second will be the velocity of air within this duct. That is the typical velocity of air that we normally use to transport the tufts. And the tufts are introduced at some point as shown in the diagram, and they are therefore moment they enter the duct, suddenly there will be acceleration on them when they are dropping within the duct. The velocity is very low, and as soon as they come into contact with the air, there will be a sudden lot of drag force will be acting on the tuft, and the tuft will be carried forward, and quickly the tuft will attain the speed of the almost the speed of the air, and it will move at a high speed towards the separating disc. Now, once the flocks or the tufts arrive at the separating disc point, the air will pass through the perforation. A separating disc we will discuss also, there are a lot of perforation within it. So, through the perforation the air can escape, they will pass through, and then they will exit from the duct. If the air contains some dust, dust will also escape through the perforations. But these flocks or the tufts will be settling on the separating disc. The disc rotates slowly, and the tufts will be then dropped down as shown in the diagram, and the separating disc that is used, we use either a Shirley wheel or a condenser cage for separating tuft from air. So, we will discuss what is a Shirley wheel and what is a condenser cage. These two are very common in the blow room line. Typical diameter of a duct could be 10 to 12 inch, and the speed should be around 12 to 15 meters per second, but should not be greater than 20 to 24 meters per second. Then there is a chance of turbulence getting created within the duct, too much of turbulence, and which can lead to formation of naps. That is the either that very high speed is not used, but at the same time very low speed also we cannot use. Then the tufts will move in a very sluggish manner. So, they will come into contact with the inner wall of the duct too frequently, and as a result there will be friction between the tuft and the inner wall, and any friction between the fibers and the and the static surface on the duct means there is possibility of generation of nappe. So, neither too slow speed of the tuft is good for us, not very high speed is good for us. Now, a Shirley wheel is shown in this diagram. It is basically a perforated disc. You show this diagram in the right hand side, the lower diagram. There are a lot of perforations on this disc, and it is placed at right angle with respect to the duct axis, and generally rotates at a speed of 70 rpm, typical speed. The air is sucked through the perforations to the other side of the disc, and the deposited cotton is carried downwards due to the rotation of the disc, and they simply fall down, because as soon as they rotate, they will come to a location where the suction is not effective, and therefore, due to gravity action, the tuft is going to fall down. That is what Shirley wheel is. It is a very simple device. The other one is a condenser case, purpose is same. You can see the diagram on the right hand side, that there is a fan, and there is there is basically a large drum, and the drum has a lot of perforation on its surface. So, an under pressure is created inside the drum, and thus in the connecting duct by a fan at one end of the drum. So, we create a negative pressure within this drum. So, this is our drum, and this drum has lot of perforations. So, either this can be connected to a suction pan separately also, or we can have a fan inside as well. So, the tuft along with the air is carried towards the cage. So, the tufts will like the air and the tuft, this mixture is coming and falling on the surface of this drum. The air will pass through the perforations, they can easily pass through, and finally, this air will be escaping this drum, and it will maybe going to the filter house, where we will be filtering this air, because the air will also contain a lot of dust. So, they cannot be just released to the outside atmosphere. We need to filter this air. The drum rotates slowly and brings the deposited fiber layer near the Doepfer roller. So, you see that yellow part that you see, it is a deposition of tufts on the surface of the drum. So, as the drum rotates slowly, these deposited tufts will be brought on the near the doffing roller or Doepfer roller. You can call it Doepfer roller, or you can call it stripper roller. So, as soon as it comes over there, this Doepfer roller is going to scrape off the layer of tufts from the surface of the drum or surface of the cage. This can be called drum, or also it is also called cage. The lower region of the drum surface is cleaned off from the under pressure in the interior, and therefore, once it comes over here, the flocks are not going to stick to the surface of the drum. There is no, I should say, that force acting between the layer of the tufts and the drum. By the time this layer of tufts which are there on the surface of the drum is nearing the Doepfer roller. On the front side, there is a suction. So, therefore, the tufts are coming, falling on the surface of the drum, and the remaining they are stuck on the drum surface. But the drum slowly rotates, it carries forward the deposited tufts on the other side, where these perforations are blocked by an interior. There is a plate over here which will block these perforations, and hence there is no force which is acting between the tuft and the drum. So, they can be easily scraped off by the Doppler roller. So, typically case diameter around 55 centimeter, speed could be around 75 rpm, and the surface speed of the Doppler and surface speed of the cage is, the ratio could be around 2.4. So, these are the things which can be changed or can be adjusted depending upon the flow rate of tuft and the kind of, that means the kind of production that we are keeping in the blow room line. The air output is typically 50.97, close to 51 meter cube per minute. That is the suction rate, the volumetric flow of air. So, the fan should be powerful enough to suck around 51 meter cube per minute of air. This is, so these two, either Shirley wheel or a condenser cage is used to separate out tufts from air. In the pressure mode of transport, what we do? The air is taken directly from the atmosphere. See, there is a blower fan on the left hand side being shown. It is drawing air from the atmosphere, and the pressurized air is blown now. The air is blown through the duct. The tufts are introduced as shown in the diagram. At the end of the pipe, air and material has to be separated, as we have discussed in the previous case, and the tufts generally falls down and the air is exhausted from the other end. Pressure systems are generally recommended when the material is introduced at one point and transported to different delivery points. That time the pressure system is generally that is what is recommended, and due to very high pressure differential, they have a great capacity than the suction type. So, in some situations this is pressure mode of transportation is used, but in our blow room line it is mostly suction mode of transport. But in some other industry, many industries, pressure mode also can be used. If you remember the air jet cleaner that we discussed, there was a blower fan there which was generating air and forcing the air to pass through a tapered duct. So, there we needed such kind of a blower fan which can generate very high pressure, so that we can transport the tuft there at a very high velocity. If you try to recall the kind of velocity we wanted in the case of air jet cleaner, that one suction pan is not good enough. So, that we had to take the support of another blower fan which was actually generating high pressurized air, and as a result the tufts were flowing through the narrow and tapered duct at a very high speed, and then there was taking certain turn, and therefore we could clean the tufts where a higher speed was required. Anyway, so these are the two modes of transport. Now, we will try to understand little bit about the flow of air and transportation of particles through it. So, very basic understanding. Now, to allow a tuft to be transported, the driving flow forces of air must be greater than the weight, the friction and the inertia of the material it is going to transport. So, in this case the material is tuft. So, the driving flow forces of air, that is when the air is acting suppose on a tuft, the force that is acting on it should be much greater than the weight of the tuft itself, friction between the tuft and the inner wall of the duct, and the inertia of the material also. So, there are three influential factors. One is suspension speed of the material is called Vs, the velocity of the air which is V, and the mixture ratio called mixture relation which is R. And what is this mixture ratio or mixture relation? It is material transported per unit time and conveyed air mass per unit time. This ratio is very important. These are the three factors which are important when you try to convey any material for that matter through duct. Suspension speed, the velocity of the air, and the mixture ratio. Let us say the flow resistance of the drag on a tuft is represented by D, that is the drag force on it, and G is the weight of the tuft. So, how much is D? D is half Cw A rho V square. This is typical formula of drag force which is acting on a particle or a matter which is within a flowing fluid. Now, Cw is the resistance coefficient of the shape. Cw may change depending upon the shape of the material. It is not only the shape sometimes matters, because the same material or same particle may have different shapes. Cw depends upon the shape. A is the flow face area of the tuft in this case, that is the area of the tuft perpendicular to the flow direction, that is the A value. So, depending upon the shape, the value of A will change. For a sphere, the value of A is always constant, but any other shape if we take, depending upon its orientation with respect to the flow direction, the value of A is going to change, and the rho is the atmospheric density. So, therefore, D is, this formula is very important for us to know, and D is half Cw A rho V square. Now, if D is G, when D and G are constant same, the velocity of the air is, we call it Vs at that time, and that is the suspension speed. That is, if I add that velocity of the air, the tuft or the particle will simply remain suspended, it will not move, it will remain suspended at a certain height. So, as long as, so that is called the suspension speed. So, as long as the velocity of the air is Vs, the tuft will remain suspended and is not going to move, and therefore, the suspension speed is influenced by the density of air. Conveying capacity will slightly increase on very cold days, as density will be more on cold days. Air density will be more when the temperature is low, and also depends on Cw. Cw in turn depends upon the shape of the particle, or in this case shape of the tuft, and also depends upon the surface roughness of the tuft or surface roughness of the particle, whatever we can say. So, Cw depends upon these two, and also we have said, so these are two important factors to remember, suspension speed upon these two, and also will depend upon the value of A, or A also can change depending upon the shape of the tuft. Tufts are generally elongated. It is very difficult to define what is the exact shape of a tuft. A tuft is not spherical or not conical or neither rectangular. We just cannot define the geometrical shape of a tuft. They are having all types of shapes, and different types of contours. Other thing is the surface of the tuft is little fuzzy depending upon how much it has been opened. So, these are the difficulties with the tuft, defining the volume or shape of the tuft. Anyway, the minimal condition for conveying is what is that the air speed in the vertical pipe must be more than the suspension speed, that is V has to be greater than Vs, then only the tuft will move, otherwise the tuft is not going to meet. So, we can find out what is the suspension speed of a tuft, and in the Bloedom line you see initially the tufts are very big in size, they are less open, they are dense also. As the tufts are opened more and more by the successive machines, the density of the tuft will reduce, they become more open or more voluminous, at the same time their weight also reduces. So, the suspension speed is going to change. Anyway, we must remember that the velocity of the air has to be greater than the suspension speed, then only we will be able to transport the tuft. The other thing is the pressure loss during conveying. So, when we try to convey the tufts, we need certain amount of force, and this force is created because of the pressure. Now, what happens is that when the pressure is high, the velocity will be more, the tuft can be carried forward very fast. But there are many reasons why the pressure drops down while we convey a fluid through a duct, or we are conveying some solid matters through a duct with the help of fluid. What are the causes of pressure loss? One is the acceleration of the material. As soon as the material enters the conveying duct, there is a sudden acceleration, because we have to spend some energy to change the velocity of the particles from almost 0 or whatever is initial velocity to the velocity of the air or fluid. So, that will need some energy, and because of this there will be a drop in pressure. The other thing is head loss due to elevation change, that is the conveying duct not necessarily is always horizontal, somewhere it will be going vertical also. Because of whatever, when it goes vertical, then we have to put extra energy to move the particles in the vertical directions. Because of this, there will also a head loss or pressure loss. Then there is a friction loss of the air. The air is coming into contact with the inner wall of the duct or pipe, and this friction we have to overcome, and because of this there will be some loss in pressure. And the third thing, and another part is the material friction could also be there. So, the material as it is flowing through the duct, it will hit the inner wall sometimes, and therefore, whenever it hits the inner wall, the velocity will reduce or it will be retarded, and again it will be picked up by the moving air, it will be accelerated. So, retardation and acceleration will be continuously there on the particles, and due to this there will be also a loss in pressure. The last point is the bend or the elbow or the fitting loss. Wherever there is a bend, the air has to take a turn, and hence there is a loss of pressure. So, there are many reasons why the pressure will be lost as soon as we feed the material in the duct. Therefore, at any point of the conveying pipe, a minimum air velocity, we call it the critical speed, is needed which varies according to the characteristics of the material and usually between 10 to 30 meters per second. So, the velocity of the particle will change, it is directly connected to the pressure difference. So, if the pressure difference changing along the length of the duct, there will be a change in the velocity of the particles, or in this case the velocity of the tuft. Therefore, the velocity of the tuft will, or the tufts will be slow down, and if the airspeed falls short of this critical speed, then the material will not be able to move properly. So, it will fall down as shown in this diagram. You see the lower diagram, the particle is coming and hitting the inner wall. So, whenever it hits, there is a retardation of the particle, and again it will rebound back, picked up by the air, again air will going to increase the velocity, there will be acceleration. But if the speed is too low, the material will deposit on the pipe bottom, and if excessive material deposits, that could be blockage. This possibility could be there. So, to avoid this blockage, we have to make sure that when these tufts are carried forward, the velocity of the tuft throughout the duct remains much more than the critical speed. Otherwise, there is a chance of blockage with time. Typically, some data is given here, like transport of fiber flocks from machine to machine. The typical air velocity is 8 to 10 meters per second that we will keep. It could be sometimes more also. Air discharge is 0.4 meter cube per second or 24 meter cube per minute. The waste from brood room to silo, you need a higher velocity 15 to 25 meters per second, and the air discharge rate is more or less similar. The micro dust of fiber fragments, we need a velocity 12 to 15 meters per second. So, these are the typical velocities that we keep or is required in the transport duct, and the typical duct that we use in our blown home line at different locations, there are different ducts. See, we use 110 mm, 160 mm, 220 mm, 300 mm, 400 mm, all depends whether you are trying to transport the tufts or you want to transport the waste from the brood room line, or you want to transport the micro dust. Depending upon that, we can choose the right diameter of the transport pipes. So, some typical values are given here. Now, this is an important point or important analysis which you should all try to understand properly, the pressure velocity relationship. Now, according to Bernoulli's theorem, now this theorem you must have studied in basic physics, we are writing the same formula again, P1 by rho g plus V1 square by 2 into g equal to P2 by rho g plus V2 square by 2 g. We are writing here this equation, and the pipe is a duct which is horizontal, therefore, elevation is same, and hence the rho g h part which you generally see in the physics book, that is not there, because we are analyzing a situation where the duct is perfectly horizontal with respect to the floor. So, from here, from equation 1 we can write equation 2. Equation 2, that is we had g are there both on the left and right hand side. So, we can omit G. So, P 1 rho V 1 square by 2 equal to P 2 rho V 2 square by 2. Rho is the density of air. So, we are assuming that there is no change in the density of air. So, P 1 minus P 2 becomes rho by 2 V 2 square minus V 1 square by, all right. Now, if V 1 is 0 at the entry point, the velocity is 0 and P 1 and P 2 we write is as delta P pressure difference. So, that becomes rho V 2 square by 2, and from here therefore, V 2 square is equal to 2 delta P by rho, where rho is density of air. Typical density of air is 1.225 kg per meter cube, and hence V 2 is 1.414 root over delta P by rho. So, if I choose the rho value to be 1.225, then this becomes square root of rho becomes 1.106, and therefore, the relationship becomes V 2 is 1.27 root over delta P, that is the pressure difference or pressure differential. So, the velocity within the duct can be found out if I know what is the value of delta P. So, V 2 is 1.27 root over delta P. This is equation number 6. An example has been given here, that let us say for a pressure difference of 5 kilopascal, the density of air is 1.27 kg per meter cube. What will be the velocity of air flow? So, we use the same equation, 5 kilopascal is 5000 Newton per meter square. So, we can find out what is V 2 square. We find it out, it is 802.6 meter square by second square, and therefore, V 2 is going to be 28.33. In this particular example, if the pressure difference is 5 kilopascal, the air velocity is going to be 28.33 meters per second. The other thing is power required by the blower fan. How much power is required? We are very much concerned about the energy always, how much energy is consumed by the machines. We always need energy efficient machines. So, we also see there are so many blower fans which are working in the blow room line, and therefore, we have to also see how the energy is connected to the operational parameters. So, higher horsepower is required of the blower to create conveying pressure. Electrical power N required of the blower depends upon the volume flow rate of air, that is V, the pressure that we require delta P, and the efficiency of the blower, which is eta. And the equation is the power is V volume flow rate into delta P by eta. So, this is the power requirement. Now, the volume flow rate is dependent on the cross section area of the duct A and of the velocity of air that we need to carry the tufts. So, capital V is a function of small v air velocity and the cross sectional area of the duct. So, capital V is A small v, which is pi d squared by 4 into V, where d is the duct diameter, and hence we replace capital V by this value, we get capital N pi d squared by 4 small v delta P by eta. So, equation 9 gives us how much power we required and how this power requirement is connected to different parameters. From the Bernoulli's energy equation, the pressure loss in the pipe at the turbulent flow is proportional to the square of the air speed. So, delta P is proportional to V square also. Therefore, N, the electrical power requirement, is proportional to V cube, that is the velocity of the air. Hence, you see that the power requirement increases disproportionately with increase in small v, that is the speed of the air. So, if we can reduce the air velocity requirement for transporting the tufts, we have a huge gain in the power requirement of the blower fan, because N is proportional to V cube. So, lesser the air speed, lot of saving of energy. So, this is all about the pneumatic transport. Now, what are the disadvantages of pneumatic transport? One is the creation of the vortex inside the ducts, and as a result the flux or the tufts will get entangled, resulting neb formations. So, this possibility is there, and other thing is the long duct also create nebs due to friction between the inner wall of the duct and the tufts. So, long ducts is also a source of problem, because we can't avoid the collision between the fibers, the tufts and the inner wall of the duct. There will be always some collisions, and as a result there is a chance that fibers will get entangled, and entangle may lead to finally formation of nebs. Therefore, these are the typical disadvantages. So, what we try to do is to reduce the duct length. The other problem is there is the bends also. So, we also try to reduce number of bends. Every bend is also a source of friction between the fibers and the inner wall. Wherever there is a bend, the tufts will go and hit the wall of the bend, and it basically means that there is a chance of friction and hence chance of formation of nebs. So, these are the difficulties or the problems, or you can say disadvantages, but we can't help, because we have to transport tufts from one machine to other, and only there are two possibilities are there. Either you use lattice or conveyor when we go for slow speed, that is okay, but when you have to transport them at very fast speed, then we have to use air only. Okay. So, with this we close this particular lecture, and if we have some doubts we can take it up later on. With this, thank you.